Hello, in this video we'll be going on an introduction to multivariable calculus, or basically more specifically the differentiation of functions that have more than two variables. So this is a pretty advanced topic. I wouldn't go forward in this video if you don't know how to differentiate or know some calculus. If you've just been watching my videos on this channel, I haven't fully gone through the entire calculus just with single variable, with two variables yet. If you're learning strictly off that playlist, I wouldn't watch this video, because this video is for people that are very advanced with their calculus, that have just finished high school, because this is university level mathematics. You want to get assessed on this at school, it will probably appear in an engineering class, or pretty much any algebra or calculus class in university. So this is basically the start to vector calculus, etc. So today we're just going to take a look at a function with basically where it requires two inputs to receive one output. So before we dealt with just a Cartesian axis like this, where you had x and y, and let's say you had some curve here, y equals f of x. So if you put in an x value here, you'd get out a y value here. Instead of having f of x where you just have one input, we're going to switch that and we're going to think of a whole new idea. Think of f of x and y, where it requires an x and a y value to basically get out a number. So in other words, we were dealing with curves. So if you have one input and you get another output, you get a curve pretty much. But with multivariable calculus, instead of having a curve, I just want to think just think of this. So imagine we get this whole axis, right? And we add a z-axis to it. So I'm just going to draw, this is our x, this is our y, and this is our z-axis, okay? So instead of so over here we had one x value gave us a y value, it was a point on a curve. Here, if you have one x value and you have one y value, it gives you a height, okay? So in other words, instead of dealing with a curve, you're dealing with a surface, okay? Can you see how that works? So basically, if you get an x and a y point, you basically get a height on the surface. And if you get a bunch of them together, all these points together, you create a surface. So in multivariable calculus, we're dealing with curved surfaces rather than just a curve or a line or any, pretty much. Think of it, it's 3D now. So this is whoopsie daisy. This is, I just went all the way. This is 3D, okay? So if you get an x and a y value, you get a height, a z value, okay? Now, here's an idea. We talked about a tangent line in just one input, one output. We talked about a tangent line as the derivative. However, in 3D, which way are we looking? Because you could have a tangent line going this way, you could have it going that way, etc. It becomes based on orientation pretty much. And this is where this idea of partial derivatives comes in. So with a normal derivative, so we have normal derivative, we have d over dx. With a partial, we basically change the notation slightly. We use this kind of symbol here as partial, okay? So I'm just getting used to your notation. So basically, if you want the gradient at a certain point, there's two ways you can look at it. You can look at it from the x direction, so you can have the line going this way, or the y direction, the line going that way. If you look at it from the x direction, no matter where you are on the x line here, as long as you move across where the tangent is, y will be constant. The y value will be a constant value. Similarly, if you're looking at the gradient from the y direction, you move along the y direction, the x value will be constant. So basically, if you have, let's say you have z equals x squared y, and you wanted to find the partial derivative with respect to x, okay? So you just differentiate this whole thing with respect to x, right? Except you would keep the y, as a constant. You treat it as a constant value, okay? So all you're doing is just differentiating with respect to x. So actually, I'm just going to move this whole diagram out the way a bit and put that there. Right? That's a y. So if you're differentiating with respect to x, you treat the other variable as a constant. Okay? So delta z, delta x, the partial derivative of z with respect to x, is just going to be equal to 2xy. You see how the y didn't change at all? Because you treat it as a constant. Because no matter, if you're looking at the steepness in the x, with the partial derivative with respect to x, the y value is treated as a constant. Okay? Similarly, if you want to find the partial derivative with respect to y of this particular function, you would treat x squared as a constant. Okay? So you'd only differentiate with respect to y. Now, if you differentiate just y, that goes to 1. So the partial derivative of z with respect to y would just be x squared. Okay? So that's how you basically do a partial derivative of a function. If you want a better explanation of this whole idea here, I'm going to do a separate video, but this video I'm most likely going to be focusing on this idea of how to actually differentiate these functions. And I think I did a pretty good job with explaining this here, but I'm going to probably do a more in-depth video. I'll probably use like GeoGebra to show why the other variable is always a constant. Okay? Alright, let's get started with our first question. Alright? So just question 1. I know you can see question 2, but don't have a go at 2. Well, actually, if you understand this already and you're just using this video as a problems video, I'd go ahead and start doing the problems. But just have a go at question 1. So find the partial derivative of z with respect to x, and find the partial derivative of z with respect to y. So if you want to have a go at this, feel free to pause the video and have a go, and I'll solve it in just a second. Alright, let's straight off the back. Let's do the partial derivative of z with respect to x. So we're going to write partial derivative of z with respect to x, and partial derivative. And we're going to differentiate. Oh, my pen didn't work. We're going to differentiate this entire thing with respect to x. And we're going to treat y as a constant, okay? Because we're taking the partial derivative with respect to x, okay? So we're going to have delta z over delta x equal, if you differentiate, so the only thing I'm looking at is the x cubed. So I'm just differentiating that. I don't care what this stuff is. It doesn't matter. It's not an x. It's not important to me, so I don't give a damn. So I'll differentiate x cubed. You bring the 3 down the front and subtract by 1. But if you're doing multivariable calculus, I hope you know the power rule. If not, I just made a video on it. So 3x squared y over 6 divided by 3. 3's cancel. So this whole thing simplifies down to x squared and y to the 6. That's the partial derivative with respect to x of this function here. Are we done? No, we're not. We just gotta find the partial derivative of this function with respect to y. So the partial derivative of z with respect to y, differentiate this entire thing with respect to y. Now, if I'm doing that, what does that mean? I treat x as a constant, okay? Don't give a damn about the x. If it's not a y, it's not important, okay? So differentiate this with respect to y. So we're going to have delta z over delta y is going to be equal to 6y to the 5 x cubed over 3. That whole thing can simplify to 2 on the top because 6 divided by 3 is 2. So delta z over delta y is equal to 2y to the 5 x cubed. Boom. Done. Alright, let's have a go at question number 2. Alright, so feel free to have a go at question number 2 and then I'll start solving it. Alright, so same question as before, just a different function. Find the partial derivative of z with respect to x, and then find the partial derivative of z with respect to y. So just going to differentiate with respect to x. So we can go delta z delta x is equal to partial derivative of x over y. I don't care about the y, I only care about the x. If I differentiate with respect to x of x, that's just 1. So this whole thing is going to simplify to just 1 over y. Okay? Because if you just take the normal derivative of x, that's just 1. So therefore the partial derivative of x is still 1. That doesn't change. The laws of differentiation don't change with partial derivatives. You just treat the other variable as a constant, or how many variables you have. This works with many functions. You can have functions with 3 inputs and give a 4th output. I don't know how you'd visualize that, but it works. Okay? Alright, first one is done. We've got that. Now we're going to find the partial derivative of z with respect to y. So delta z over delta y, and take the whole partial derivative with respect to y of x over y. Alright, x is a constant. We're just looking at the y. Recall what happens if we differentiate 1 over x. What does that turn into? Okay? Well, you have to think of it, think of this whole thing, instead of being 1 over x, that's the same as x to the negative 1, right? Okay? So we can think of this whole thing here as just differentiating hold on, sorry, it's taking a bit. The same as differentiating this. Okay? Don't care about the x. I'm going to say that a lot. I won't care about the x unless I'm differentiating with respect to x. Bring the negative 1 down the front and subtract by 1. So you're going to have delta z over delta y is going to be equal to negative x multiplied by y to the negative 2. Simplifying that whole thing. So delta z over delta y is equal to negative x over y squared. That is the partial derivative of z with respect to y. Boom, boom, boom. We've done it. Alright, let's move on to question 3. If you have any questions at all in this video, please leave some in the comments and I will try my best to answer them. If you want to find out where I got all these questions from, I just bought a book recently on Essential Skills Workbook on multiple variables. It also has a lot of stuff on vector calculus, which I'll be slowly starting. I'll just basically be doing every question in this book and uploading it to the channel because I think this book is fantastic for multivariable calculus, and I also bought one for just single variable calculus as well that I'll be uploading. Okay, so let's have a go at question 3. So if you're ready, just have a go at it and then I'll start solving it. Alright, so notice how they don't use z's. They can use an f, they can use a u. If you get to partial differential equations, they use u a lot instead of f and z. But f, z, and u are typically the more common ones. You can see down here they use a w, but that's because they just want to get in your head. It doesn't matter what the symbol is as long as the process is the same, pretty much. So let's differentiate this with respect to x. So partial derivative with respect to x. Now the y is under a square root. Does that matter? No, it doesn't. You know why? Because y is a constant. We don't care about y. So the partial derivative of f with respect to x, differentiating just x with respect to x is 1. So the whole thing is just the square root of y. Okay? Alright. We've done that. Let's do partial derivative of f with respect to y. Alright, now, oh, that is terrible. Partial derivative of y over x square root of y. Alright, now we care about that square root of y, because now we don't care about x, because we're differentiating with respect to y. Notice how I just keep telling you that don't care about the other variable if you're differentiating with blah blah blah, etc. Alright, square root of y is the same as y to the power of a half, okay? So change how this looks. Partial derivative of f with respect to y is the same as differentiating with partial derivative of respect to y is the same as x to the y to the half. Bring the y down the front, subtract, bring the half down the front and subtract by 1 to the power, so you're left with this. You're going to have a half x y to the negative half, because a half minus 1 is negative half. Now we can start tidying that up. Recall if you have whoopsie daisy, if you have y to the negative half, that's the same as 1 over y to the half. And recall y to the half is the same as square root of y, so that whole thing simplifies to 1 over the square root of y. So therefore we can simplify the partial derivative of f with respect to y is equal to x over 2 the square root of y. Boom. Too good. Alright, let's go on to the next question. Yep, if you have any questions, leave some in the comments. Alright, if you have a question 4, feel free to have a go, and then I'll start solving it. Alright, so they've switched it up this time. They've used W instead of Z or F. They're being a bit fancy because they just want to try and confuse you. Unless they specify, never mind, don't worry about that. That's not important in this video. Alright, let's just take the partial derivative with respect to t. So, partial derivative of w with respect to partial derivative of t. That is terrible writing. I don't know why my computer is lagging. Partial derivative with respect to t. So I only care about the functions that have t in it. And just looking at it, there's only one I care about, this, okay? So we're only going to differentiate that. We don't care about cos u, but cos u can stay. Now, what happens if you differentiate sine? That turns to cos, doesn't it? Okay? So this whole thing is going to be delta w over delta t is going to be equal to cos, cos t cos u. Boom. Alright? Now let's find the partial derivative of w with respect to the partial derivative of u. So partial derivative of w Alright, what do I care about? Looking for my u. My u's in here, my u's not in here. I don't care about my sign. Alright, so differentiating cos, that turns to negative sine. And we don't have any coefficients in here, so it's just going to be just negative sine u. So differentiating that, partial derivative of w with respect to u is equal to negative. So this negative is coming from when I differentiate the cos here. Negative sine t sine of u. So this negative sign came from here when I differentiated from here. Okay, cool. Alright, that's that question done. Let's move on to question 5. Righto. So if you haven't got this one is I would say it's a bit tricky, kind of, if you've never done stuff like this before, because differentiating can get a bit confusing with two variables. You just gotta take your time with it. Don't rush it, because yeah, pretty much just take your time. Do that with all your math. Alright, so if you haven't got question 5, feel free to have a go, and then I'll start solving it. Alright, so this one has a exponential and a log, okay? That doesn't matter, we know how to differentiate those. And even though it's multivariable calc, it might get a bit scary, but we can still do these. So let's just differentiate with respect to x. So partial derivative of g with respect to x. Just differentiating this entire function with respect to x, okay? Alright, so e to the y, do I care about that? No, that's a constant. What happens when we differentiate? We're going to have to differentiate this log because it's got an x in it. What happens if we differentiate a log? Recall, so if you have, if you want to find the derivative of log x, that's the same as 1 over x. That's 1 over x is the derivative of log x. So just differentiating this, delta g over delta x is just e to the y times by 1 over x. And you can simplify that, so delta g over delta x is just e to the y over x. Boom, that's not that hard, is it? all you're doing is taking ideas you got from first year calculus and just putting it into the third year calculus. The only difference is we're using different symbols and it's a bit more complicated, but it's all the same stuff. You got this. Alright, so let's have a go at the second part of this question. So, partial derivative with respect to y. Differentiate this entire thing with respect to y. Okay? Why is my pen lagging? Sorry, guys. Partial derivative. Sorry, it's like it always does this. Alright. Differentiating with respect to y, I only care about things with y in it, so I don't care about the log x. I only care about this e to the y. What happens if we differentiate e to the x with respect to x? You just get e to the x. So if we differentiate with respect to y, e to the y, it just stays as e to the y. So we actually don't have to change anything at all. Why is it green? I selected black. So delta g over delta y is just the same as g, or e to the y log of y. We don't have to log of x. We don't have to change anything. Alright, cool. Those are those questions done. Let's move on to the next one. So have a go at question 6. Alright, question 6. It's a bit bulky, but you can do it. So let's just have a go at differentiating with respect to bless me. Let's differentiate with respect to x. So delta z over delta x is just differentiating this whole thing with respect to x, okay? Find the partial derivative with respect to x, okay? That just means we ignore our y. We treat y as a constant, okay? Alright, differentiating x to the power of 4. Bring the 4 down the front, subtract 4 minus 1 at the top. So we're going to have delta z over delta x is going to be 4x cubed. Alright, this here, we don't care about our y squared, we just leave that alone. Just differentiate this thing here. So that's going to be, bring the 2 down the front, we're going to have 4x, and instead of the y squared because it's a constant, boom. That's that derivative done. Wasn't too hard. Alright, let's have a go at differentiating with respect to y. So the partial derivative of z with respect to y, taking the partial derivative with respect to y of x to the 4 plus 2x squared y squared. Alright, now we're going to ignore our x's, only looking at this y here. So if we find the partial derivative of y, if we differentiate this with respect to y, the whole thing turns to 0. So we're going to have delta z over y is going to be equal to, that whole thing turns to 0, so we don't write anything down. Differentiating y squared, bring the 2 down the front, so we're going to have 4x squared to the y. Boom. Too good. Alright, have a go at question 7. This one is a bit tricky, but it's the same principle as before. You might have to use a certain rule that you've learnt previously. Alright, so feel free to pause the video and have a go. Alright, straight off the back, we're doing with partial derivatives, but we're going to have to use chain rule. So recall chain rule, if you differentiate, if you have a function, if you have, hold up, I don't know why that went up there. If you have a function inside another function, the way you differentiate that is you diff the outside and you multiply it by the differential of the inside, okay? So if you're differentiating a function inside another function, you diff the outside, leave the inside, then diff the inside on the outside, okay? Alright, so find the partial derivative of u with respect to p. Let's just do that. So delta u over delta p differentiates whole thing with respect to p. And they've used p's and q's to confuse you, but this is no more than just a simple calculus problem. Okay? So what am I going to do? I'm going to differentiate the outside. So recall square root of blah 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 is the same as blah blah blah, all to the power of a half, alright? So where we differentiate the outside is we bring the half down the front, so we have a half, still have the inside, so p squared minus q squared, a half minus 1, the same as negative a half. Now we differentiate the inside with respect to p, so our q squared goes bye-bye. When we differentiate p squared, why does it keep changing colors? If we differentiate p squared, that's going to be 2p, so multiply that by 2p. A half times 2, it just cancels, so we're going to be left with delta u over delta p is equal to p over the square root of p squared minus q squared. Okay? Boom. That's the first part done. Now we're going to use exactly the same method as we did just then. We're going to use chain rule for finding the partial derivative of u with respect to q now. So it's the exact same thing, except we treat p as a constant this time. So delta u with delta q, differentiate this entire thing with respect to q. So delta u, delta q, it's going to be a half p squared minus q squared, which is negative a half. Differentiating this, because this turns to 0 when we diff it, that's going to be multiplied by negative 2q. So simplifying this entire thing, we're going to have negative q over the square root of p squared minus q squared. Boom! Too good. Alright, let's move on to the next one. Last question of the video. Alright, 8. Have a go at that one. Alright, so straight at the back, we're going to have to use chain rule. Alright, so differentiate this entire thing with respect to just t. So if you have delta h, delta t, differentiate the entire Why is it rubbing out? I don't understand. I'm just going to start writing down here. So you have delta h, delta t. Hold up, just give me a second, my computer's lagging for a sec. Alright, let's have a go at it for a third time. So delta h, delta t, differentiate this entire function with respect to t. So you have to diff the outside function. It's not letting me write at all. It's really annoying. Right, hold up. We just might have to give it a second. So if you want the partial derivative of h, I have no idea what's going on with this. I might just have to stop the video. Sorry if you want to have a... Actually, in the next video, I'll show you the solution to this one. So if you want to have a go at it, just feel free to have a go, because my computer's lagging. Alright, thank you for watching. I hope you start to learn stuff. I'm sorry to cut this video short. It's just my computer isn't that strong, so I'm going to have to stop the video now. Alright, so do this one for homework, and I'll show you the solution in the next video. Alright, thank you.